الله الرحمن الرحيم.
I'm Professor Carney, and the topic of this video is parametric equations. Parametric equations will give us an alternative way to generate curves and represent functions. Perhaps most usefully, they will also allow us to represent trajectories or paths of moving objects in space. Parametric equations have the form x equals f of t and y equals g of t, where f and g are given functions and the parameter t typically varies over a specified interval. A is less than or equal to t is less than or equal to b. The parametric curve described by these equations consists of the points in the plane x, y equal to f of t, g of t for a less than or equal to t less than or equal to b. To this point, we have been used to functions of the form y equal to capital F of x to describe curves in the xy plane. By comparison, parametric equations describe x and y separately in terms of a new variable, or parameter t, as x equals f of t and y equals g of t for functions f and g. It can be helpful to think of the parameter t as time, and for each time t, f and g determine the location of a point, x, y. As an example, let's graph and analyze the parametric equations x equals f of t, which equals 2 times t, and y equal to g of t, which equals 1/2 t squared minus 4, for the interval 0 less than or equal to t less than or equal to 8. Plotting points can help with visualizing a parametric curve, and here is a table of values showing x and y for the whole number values of t between and including t equals 0 and t equals 8. For example, when t equals 6, x equals 12, and y equals 14, which can be found by evaluating the given parametric equations when t equals 6. Now we can plot the xy pairs on a coordinate axis and connect the dots to create a graph for the parametric equations. In this case, the curve looks like a portion of the right half of an upward-facing parabola with vertex 0, -4, which corresponds to t equals 0, and ending at the point 16, 28, which corresponds to t equals 8. Using the interactive figure, we can highlight the remaining table data and locate the points x, y. For example, t equal to 1 corresponds to the point 2, -3.5, and the point t equals 2 corresponds to 4, -2, and so forth, all the way up to t equals 8, which we know corresponds to the point 16, 28. Now going back to t equals 0 and the point 0, -4, we can also generate the whole curve using the interactive figure. Or we can trace the complete path as t increases from t equals 0 to the final value of t equals 8, including all real numbers or decimal t values between 0 and 8. Notice that the values of the parameter t do not appear in the graph, but the only signature of the parameter is the direction in which the curve is traced. In this case, the curve is traced out upward and to the right. This leads us to the following definition. The direction in which a parametric curve is generated as the parameter increases is called the positive orientation of the curve and is indicated by arrows on the curve. In our example, we can indicate the positive orientation or direction of the motion by using arrows, which trace the curve as we move up and to the right. The fact that parametric equations allow us to represent this motion will be a useful tool moving forward. In this example, we're asked to consider the parametric equations where x equals t cubed minus 1, y equals 5t plus 1, and -3 is less than or equal to t is less than or equal to 3, and do the following. A, make a brief table of values of t, x, and y. B, plot the xy pairs in the table and the complete parametric curve, indicating the positive orientation or the direction of increasing t. C, eliminate the parameter to obtain an equation in x and y, and D, describe the curve. First, Part A asks us to make a brief table of values of t, x, and y. Since negative 3 is less than or equal to t is less than or equal to 3 for our parametric equations, it is reasonable to determine x and y for all integer values of t between and including negative 3 and 3. That is, t equals negative 3, t equals negative 2, t equals negative 1, and so forth, all the way up to t equals 3. For a given value of t, we can determine x and y by evaluating the parametric equations. For example, when t equals negative 3, x will be equal to negative 3 quantity cubed minus 1, which equals negative 27 minus 1, which equals negative 28. And y will be equal to 5 times negative 3 plus 1, which equals negative 15 plus 1, or negative 14. Now that we have x and y, we can enter those values into the first row of our table. We can determine the remaining values of x and y to complete the table as shown. For example, when t equals 1, x will be equal to 0, and y will be equal to 6. In Part B, we're asked to plot the xy pairs from our table and use them to complete the graph of the parametric curve. First, we can show the points in our table on an xy coordinate axis and label the points with their corresponding t-value. The points are plotted roughly in a window for x between negative 30 and 30 and y between negative 15 and 15, corresponding to the range of both the x and y values from our table. The first point, corresponding to t equals negative 3, or the xy point, negative 28, negative 14, is plotted in the lower left, and the points rise and move to the right as t increases based on our table. Next, we can connect the dots to fill in the graph of the parametric curve, and in this case, our curve appears to have the shape similar to a cube root function. We can indicate the positive orientation, or direction of the motion, by drawing arrows on the curve in the direction of increasing t, which in this case is as we move up and to the right on the graph. In Part C, we are asked to eliminate the parameter and obtain an equation in x and y. One method for eliminating the parameter involves solving for t in one of the equations, and we may use either the x or the y equation. In our example, we can solve for t easily in either equation, but we will use x equals t cubed minus 1, as this will give our final answer as a function of x. Thus, if x equals t cubed minus 1, x plus 1 will equal t cubed, or t cubed will equal x plus 1. And taking the cube root of both sides, this will give us t equals the quantity x plus 1 to the 1/3. Now that we have solved for t, we can substitute into the y equation. Since y equals 5t plus 1, this will give us that y equals 5 times the quantity x plus 1 to the 1/3 plus 1, and we have eliminated the parameter. And in this case, our answer is in the form of a function of x. To be complete, however, we should think about the interval for x, or the independent variable, with our function, as our parametric equations do not describe the complete curve. Recall that negative 3 was less than or equal to t was less than or equal to 3. Thus, by cubing, this gives us negative 27 is less than or equal to t cubed is less than or equal to 27. And by subtracting 1, we get negative 28 is less than or equal to t cubed minus 1 is less than or equal to 26. Since x was equal to t cubed minus 1, this tells us that negative 28 is less than or equal to x is less than or equal to 26. And thus, by eliminating the parameter, we have that y equals 5 times the quantity x plus 1 to the 1/3 plus 1, where negative 28 is less than or equal to x is less than or equal to 26. In Part D, we're asked to describe the curve. And in this case, our answer is a scaled and shifted version of the cube root function y equals cube root of x. Being able to parameterize certain curves, including circles and lines, will be important for some of our later work in calculus. The parametric equations of a circle are given by x equals x naught plus a times cosine of the quantity b times t, and y equals y naught plus a times sine of the quantity b times t, where x naught, y naught, a, and b are constants, with a not equaling 0. Describe a circle centered at x naught, y naught, with radius equal to absolute value of a. If b is greater than 0, then the circle is generated in the clockwise direction. So why do these parametric equations give a circle? Solving the parametric equations given for both cosine of the quantity b times t and sine of the quantity b times t gives us x minus x naught all over a equals cosine of bt, and y minus y naught all divided by a equals sine of bt. Now squaring both sides would give us x minus x naught all over a quantity squared equals cosine squared of b times t, and y minus y naught all over a, the quantity squared, equals sine squared of bt. Now adding both equations together would give us x minus x naught all over a, quantity squared, plus y minus y naught all over a, quantity squared, equals cosine squared of bt plus sine squared of bt. And then by applying the Pythagorean identity, we know this equals 1. Finally, we can multiply both sides of our equation by a squared. And this would give us x minus x naught, quantity squared, plus y minus y naught, quantity squared, equals a squared, which we can recognize as a circle with center x naught, y naught, and with radius absolute value of a. It is common to use b equal to 1 and a positive when parameterizing a circle. Thus, x equals x naught plus a cosine t, and y equals y naught plus a sine t for 0 less than or equal to t less than or equal to 2 pi, where a is positive, will describe a complete circle centered at x naught comma y naught with radius a and generated exactly once in the counterclockwise direction. For example, the parametric equations x equals 4 cosine t and y equal 4 sine t for 0 less than or equal to t less than or equal to 2 pi will parameterize the circle centered at 0, 0, or the origin, and with radius 4. We can graph the circle on an xy axis as shown, and using the interactive figure can indicate the positive orientation or the direction of the motion. Notice that t equals 0 corresponds to the point 4, 0, or to the point on the circle directly to the right of the center of the circle. Because x equals 4 cosine t and y equals 4 sine t, we can think of t as the angle theta measured from the positive x-axis. As t, or the angle, increases, we trace the circle in a counterclockwise direction, and we have completed one full revolution when we get to t equal to 2 pi, or 6.28 approximately. Next, we will consider the parametric equations of a line, namely x equals x naught plus at and y equals y naught plus bt for negative infinity is less than t is less than infinity. This is where x naught, y naught, a, and b are constants with a not equal to 0. And in this case, our parametric equations will describe a line with slope b over a passing through the point x naught, y naught. In the case a equals 0 and b is not equal to 0, then the line is vertical. So why do these parametric equations give us a line? First, notice that if t equals 0, then using our equations, we get that x equals x naught plus 0, or x naught, and y equals y naught plus 0, or y naught. This corresponds to the point x naught, y naught being on the line. Second, if the slope of the line is given as b over a, which equals delta y over delta x, then we can look at our parametric equations again. and every time t increases by 1, a, or delta x, where the change in x is added to x, and b, or delta y, where the change in y is added to y, to give a new point on the curve. This is analogous to our definition of the slope of a line, and thus the resulting curve must also be a line. We should also point out that parameterizations are not unique, and in this case we can use any ratio b over a as our slope. That is, if k not equal to 0 is constant, the numbers a and b may be replaced with k times a and k times b in our formula. The resulting equation will describe the same line, although it may be generated in a different direction or at a different speed. As an example, consider the line through the point 2, 1 with slope equal to 1/3. One possible parameterization is x equal to 2 plus 3t and y equal to 1 plus t for negative infinity less than t less than infinity. Notice that using a and b from our parameterization gives us that b over a equals 1 over 3, which matches our desired slope, or delta y over delta x. We can graph the parameterization on an xy axis as shown, using x values between -6 and 8 approximately, and y values between -2 and 5 approximately. The parameter t equal to -2 corresponds to the point with coordinates x equals -4 and y equals -1. As t increases, we trace the graph rising to the right, thus indicating the positive orientation. This seems reasonable because if we look at our equations for x and y, or x equals 2 plus 3t, and y equals 1 plus t, as t increases, both x and y must increase, which corresponds to moving to the right and up on the graph. Another possible parameterization for our line would be x equal to 2 minus 6t and y equal to 1 minus 2t, for t between minus infinity and infinity. Using a and b from our parameterization, b over a now equals -2 over -6, which also equals 1/3, which should be our slope, or delta y over delta x. Now, looking at our parameterization over the same xy coordinate axis, we notice that when the parameter t equals -1, this corresponds to the point with coordinates x equals 8 and y equals 3. As we increase t for our parameterization, we notice that we trace the graph falling to the left. This seems reasonable because if we look at our equations for x and y, or x equal to 2 minus 6t and y equal to 1 minus 2t, as t increases, both x and y will decrease, which should correspond to moving to the left and down on our graph. So in both cases, we have found a valid parameterization of the line through the point 2, 1 with slope 1/3, although they have different positive orientations or directions. While not our focus, we may also note that the parameterizations have different speeds, in that the second parameterization is tracing the line more quickly. In this example, we're asked to find the parametric equations for the lower half of the circle centered at -2, 2 with radius 6, orientated in the counterclockwise direction. Recall that we can parameterize a complete circle using the parametric equations x equals x0 plus a times cosine t, and y equals y0 plus a sine t. For 0, less than or equal to t, less than or equal to 2 pi. In our case, the center of the circle, or x0, y0, is equal to the point -2, 2, and the radius gives us a equals 6. Thus we can use the parametric equations x equals -2 plus 6 cosine t and y equals 2 plus 6 sine t. This parameterization will generate the circle in the counterclockwise direction. However, if we use 0 is less than or equal to t is less than or equal to 2 pi, we will get the complete circle. And here, we only want the lower half of our circle. So let's consider the graph of the complete circle on an xy axis. Recall that t equals 0 corresponds to the point on the circle directly to the right of the center. And as we move to t equal to pi over 2, we should have the point directly above the center, or we will have traced 1/4 of the circle. Thus, t equal to pi corresponds to the point on the circle directly to the left of the center, and if we let t increase up to 2 pi, we will generate the lower half of the circle. Thus, the interval pi less than or equal to t less than or equal to 2 pi will generate the lower half of the circle, and we have completed our parameterization. In this example, we're asked to find the parametric equations for the line segment starting at the point 3, 1 and ending at the point -3, -2. Recall that we can parameterize a complete line using the parametric equations x equal to x naught plus at and y equal to y naught plus bt, where negative infinity is less than t is less than infinity. By restricting t to a finite interval, we'll be able to parameterize part of a line or a line segment. Here is the graph of the desired line segment on an xy coordinate axis. We'll be able to parameterize the segment so that t equals 0 corresponds to the points 3, 1, and so that t equals 1 corresponds to the point -3, -2, thus satisfying the requirement that we start at the point 3, 1 and end at the point -3, -2. Computing the change in y over change in x, going from the t equals 0 point to the t equals 1 point, the slope of our line segment equals -2 minus 1 all over -3 minus 3. Thus b over a equals -3 over -6. Note, if we do not simplify the signs, we will generate our line segment in the appropriate direction. Now we can write down our parameterization using x naught equal to 3 and y naught equal to 1, since we wanted t equals 0 to correspond to the point 3, 1. And remembering, we'll use a equal to -6 and b equal to -3. We have the parameterization, and we'll let x equal 3 minus 6t and y equal 1 minus 3t. For 0 is less than or equal to t is less than or equal to 1. To check that we have parameterized the line segment in the correct direction, notice that if t equals 0, x will be equal to 3 and y will be equal to 1. And also if we let t equal 1, then x will equal 3 minus 6 or -3, and y will equal 1 minus 3 or -2, and we have the desired parameterization. In this example, we're asked to find the parametric equations for the left half of the parabola y equal to x squared plus 1, originating at the point 0, 1. Here's the graph of the parabola on an xy axis. Notice the parabola opens upward and the vertex is at the point 0, 1. In general, one can easily parameterize any curve of the form y equal to f of x using the parametric equations x equal t and y equal f of t for an appropriate t interval. In our example, if we try x equals t and y equals t squared plus 1, where negative infinity is strictly less than t is less than or equal to 0, since we want the left half of the parabola, we generate the curve in the wrong direction. In particular, As t increases, we trace the curve down and to the right, ending when t equals 0 at the point 0, 1. We wanted to originate at this point, however. While care should be taken, many times we can reverse the direction of a parameterization by replacing t with negative t in our equations. Doing that here would give us x equals negative t and y equals negative t quantity squared plus 1. We're simplifying x equals negative t and y equals t squared plus 1. To continue to generate the left half of the parabola, we can change our interval to 0 is less than or equal to t is less than infinity. Now, positive t values will give us negative x values since x is equal to negative t. And as t increases, we trace our curve starting at the point 0, 1 when t equals 0 and moving up and to the left as t increases, thus generating the left half of the parabola originating at 0, 1 as desired. Just as we can for functions, we can talk about the rate of change of y with respect to x, or dy dx, at a point on a parametric curve. The following theorem helps us define the derivative for parametric curves. Let x equal f of t and y equal g of t, where f and g are differentiable on an interval from a to b, including the endpoints. Then the slope of the tangent line to the curve at the point corresponding to t is given by dy dx, which equals dy dt all over dx dt, which equals g prime of t over f prime of t, provided that f prime of t is not equal to 0. So why should this result seem reasonable? Roughly, here's the idea. dy dx equals the limit as delta x goes to 0 of delta y all over delta x by our definition of the derivative. Dividing both numerator and denominator by delta t gives us the limit as delta t goes to 0 of delta y over delta t all over delta x over delta t. Since x was equal to f of t, as delta x goes to 0, so must delta t. This now equals dy dt over dx dt, using the definition of the derivative again, or rewriting g prime of t over f prime of t. In this example, we're asked to find an equation of the tangent line to the curve at the point corresponding to the given value of t. This is all for the parametric equation where x equals e to the t, y equals natural log of the quantity t plus 1, and where t equals 0. To find the equation of a line, we need two pieces of information: a point on the line, x1, y1, and the slope m of the line. Then we can use the point slope form, y minus y1 equals m times the quantity x minus x1. For our example, to find the point, we can calculate x and y when t equals 0. That is, x equals e to the 0, or 1, and y equals the natural log of the quantity 0 plus 1, or ln of 1, which equals 0. Thus, x1, y1 will be equal to 1, 0. To find the slope, we need to find dy dx for our parametric curve, or dy dt over dx dt evaluated at the appropriate t value. Using our parametric equations, dx dt equals e to the t, since the derivative of e to the t will be itself, and dy dt will be equal to 1 over the quantity t plus 1, using the derivative rule for the natural logarithm function. Thus, dy dx will be equal to 1 over the quantity t plus 1, all over e to the t, which simplifies to 1 all over t plus 1 times e to the t. Now, the slope of our tangent line m will be equal to dy dx when evaluated at t equals 0. This will be equal to 1 all over the quantity 0 plus 1 times e to the 0, which simplifies to 1. Finally, plugging into our point-slope equation gives us the equation of the line y minus 0 equals 1 times the quantity x minus 1, or y equals x minus 1. We can confirm our answer graphically by considering a graph of our parametric equations over the x interval from 0 to 1.5 and the y interval from negative 1.5 to 0.5. The parametric equation, shown in blue, is increasing and concave down over the interval and crosses through the point 1, 0. The tangent line, y equal to x minus 1, is shown in red and also passes through the point 1, 0, and appears to be tangent to the parametric curve as desired. Just as we have defined the arc length for functions of the form y equal to f of x, a similar definition can be made for the arc length of curves defined by parametric equations. Thus we have the following definition. Consider the curve described by the parametric equations x equal to f of t, y equal to g of t, where f prime and g prime are continuous, and the curve is traversed once for a less than or equal to t less than or equal to b. The arc length of the curve between the point f of a, g of a, and the point f of b, g of b, is given by L equal to the definite integral from a to b of the square root of the quantity f prime of t, quantity squared, plus g prime of t, quantity squared, dt. We can take a quick look at why the formula should make sense. Consider the graph of an arbitrary parametric curve as described on an xy coordinate axis, with initial point at t equals a and terminal point corresponding to t equals b. We can approximate the length of the curve by using a familiar object, or first by dividing the curve into n line segments. Next, zooming in on one of the line segments, where the difference of the x-coordinates of the endpoints is represented by delta x, and the difference of the y-coordinates of the endpoints is represented by delta y, we can determine the length of one line segment by using the distance formula. Thus, the length of a line segment equals the square root of the quantity delta x squared plus delta y squared. Next, we can do some algebra and multiply our expression by delta t over delta t. Next, we can move delta t from the denominator inside the radical, which will give us square root of the quantity delta x over delta t, quantity squared, plus delta y over delta t, quantity squared, all times delta t on the outside of our radical. This expression represents the length of one line segment. So finally, to get to the total length of the curve exactly, we'll add up the lengths of all of the line segments, and then take the limit as delta t goes to 0, which is equivalent to the number of line segments going to infinity. By the fundamental theorem of calculus, this will tell us that our arc length L is equal to the definite integral from a to b of the square root of the quantity f prime of t squared plus g prime of t squared dt. In this example, we're asked to find the arc length of the following curve: x equal to t to the fourth, y equal to t to the sixth all over 3, where 0 is less than or equal to t is less than or equal to 1. Recall that the arc length formula for parametric curves says that the length L is equal to the definite integral from a to b of the square root of the quantity f prime of t squared plus g prime of t squared dt. This is where f of t refers to x equal to t to the fourth, and g of t refers to y equals t to the sixth all over 3, a equals 0, and b equals 1. To start, we can compute f prime of t equals 4t cubed, and g prime of t equals 2 times t to the fifth. Thus, Our arc length L will be equal to the definite integral from 0 to 1 of the square root of the quantity 4t cubed, quantity squared, plus 2t to the fifth, quantity squared, dt. By simplifying under the radical, this equals the definite integral from 0 to 1 of the square root of the quantity 16t to the sixth plus 4t to the 10th dt. At this point, our integral illustrates that these arc length integrals are generally difficult, and we need something nice to happen to be able to integrate exactly. In this case, we can factor out 4 times t to the sixth from both terms under the radical. This will give us the definite integral from 0 to 1 of the square root of the quantity 4t to the sixth times the quantity 4 plus t to the fourth dt, which will equal the definite integral from 0 to 1 of 2t cubed times the square root of the quantity 4 plus t to the fourth dt by distributing the radical over the product. Now we can evaluate our definite integral by u substitution. And this was the something nice that we were looking for. We can make the substitution u equals 4 plus t to the fourth, and thus du will be 4t cubed dt. Or dividing both sides by 2 gives us 1/2 du equals 2t cubed dt, which we see in our integrand. We can also change the limits of integration. And if t equals 0, u will be equal to 4 plus 0 to the fourth, or 4. And if t equals 1, then u will be equal to 4 plus 1 to the fourth, or 5. Thus, applying the substitution gives us the definite integral from 4 to 5 of 1/2 u to the 1/2 du. Integrating, this gives 1/2 times 2/3 times u to the 3/2, evaluated from u equals 4 to u equals 5. And this equals 1/3 times 5 to the 3/2 minus 1/3 times 4 to the 3/2. Simplifying a bit will give us 5/3 times the square root of 5 minus 8/3. And we have found the arc length of the parametric curve.